scientific death.
This graph tracks two ecological crises. The first line shows exponential accumulation of global atmospheric lead. The second maps a sudden drop in stratospheric ozone. While appearing unrelated, tracing the chemistry backward reveals both converge on the exact same origin point, engineered by one man. His name was Thomas Midgley Jr. He was a highly decorated, highly respected American inventor. Midgley was hired by the automotive and refrigeration industries to solve immediate physical bottlenecks. He needed to make cars drive faster and refrigerators run safely. The Midgley paradox reveals a specific structural vulnerability in our progress. Optimizing technology for immediate industrial constraints, while lacking a framework for biological consequences, can successfully advance technology locally while engineering catastrophe globally. Midgley earned his degree from Cornell University in 1911. His major was mechanical engineering. He had absolutely no formal training in chemistry. A few years after graduating, he joined the automotive industry. Manufacturers in the 1910s and 20s faced a severe mechanical limit. It was a problem called engine knock. Inside an engine, fuel is supposed to burn smoothly, but under high compression, early gasoline would detonate prematurely and violently. This premature explosion physically rattled the cylinder walls, destroying the engine. Charles Kettering, Midgley's boss, assigned him to fix the fuel. Kettering explicitly valued what he called Midgley's intelligent ignorance. Without a background in chemistry, Midgley was willing to test compounds that a trained chemist would dismiss entirely. Applying a purely mechanical mindset to complex chemical interactions solved the engine knock, but it also established a structural blind spot that defined Midgley's entire career. Without a theoretical chemical framework to guide him, Midgley resorted to a brute force approach. Over several years, his team systematically tested more than 33,000 different chemical additives. In December 1921, they found a match. Adding a small amount of a compound called tetraethyl lead, or TEL, to the gasoline silenced the knock completely. The engines ran smoothly and efficiently. General Motors and Standard Oil immediately formed the Ethyl Corporation to mass-produce the additive. They branded their new product ethyl gasoline, deliberately omitting the word lead from their marketing to avoid public alarm. The biological cost was immediate. At early manufacturing plants in Dayton, Ohio, and New Jersey, workers manufacturing the additive developed severe lead poisoning. Dozens suffered hallucinations, and several died from exposure to what the press began calling loony gas. The Ethyl Corporation suppressed data and blamed the workers for poor safety protocols. The corporate rush to capture the gasoline market subordinated severe occupational hazards to industrial progress, proving the system rewarded immediate utility over biological safety. Worker fatalities ignited a public relations crisis. Cities like New York and Philadelphia instituted bans on TEL, and public health officials demanded investigations. To bypass the scrutiny, Midgley held a press conference. He washed his hands in a bowl of tetraethyl lead and then held the chemical under his nose, inhaling deeply to assure reporters it was completely harmless to the consumer. Midgley omitted a critical fact from this demonstration. He had recently suffered severe lead poisoning himself from prolonged laboratory exposure, forcing him to take a secret months-long leave of absence in Florida to recover. The theatrical stunt worked. By conflating the acute short-term safety of a diluted consumer product with its long-term systemic toxicity, Midgley and the Ethyl Corporation secured total market saturation for leaded gasoline. In 1928, Midgley was handed his next major industrial challenge, creating a safe chemical refrigerant. Early household refrigerators relied on gases like ammonia and sulfur dioxide. These compounds were highly toxic and highly flammable. A simple chemical leak in the kitchen could kill an entire family in their sleep. This time, Midgley abandoned the brute force method. He used the periodic table to strategically predict a completely new synthetic compound. He focused on the intersection of halogens and hydrocarbons. His team synthesized dichloro-difluoromethane, the world's first chlorofluorocarbon, or CFC. They branded it Freon 12. At the scale of a single kitchen, CFCs solved every industrial requirement. They were non-toxic, non-flammable, and chemically stable. Freon 12 rapidly replaced dangerous older refrigerants. It enabled the mass adoption of global air conditioning, dramatically reduced foodborne illness, and provided safe cooling for medical vaccines. Midgley's predictive methodology met every immediate requirement for human safety and industrial application, yet left no room to consider how these stable molecules would interact with the atmosphere. Anthropogenic disasters are often defined by latency. This is the decades-long gap between local industrial success and distributed global harm. For leaded gasoline, the latency loop operated close to the ground. Cars burned the fuel and emitted invisible lead particulates that settled into the soil. Humans ingested this heavy metal, which accumulated in bloodstreams and severely impeded cognitive development in children over multiple generations. For CFCs, the latency loop operated in the sky. Their extreme chemical stability meant they didn't break down in the lower atmosphere. Instead, they floated undisturbed for decades until they reached the stratosphere. Here, without the Earth's atmospheric shielding, unfiltered UV radiation breaks the CFC molecule apart. This releases a highly reactive chlorine atom, which systematically and catalytically dismantles protective ozone molecules. We are looking at a satellite visualization of the Antarctic ozone hole. We couldn't catch the damage earlier because the scientific capability to detect these macro-scale atmospheric effects didn't exist until the 1970s, long after the chemicals achieved total market saturation. Perfect local engineering, entirely divorced from ecological feedback loops, inevitably acts as a ticking time bomb at a planetary scale. The global reckoning eventually arrived. The EPA began phasing out leaded gasoline in the 1970s, and the international community signed the Montreal Protocol in 1987 to ban CFCs. But the extreme persistence of these chemicals means their effects lag far behind the legislation. The soil contamination and stratospheric damage they caused will take decades, if not centuries, to fully recover. Midgley's work reflects the priorities of his era. He was an incredibly competent engineer, fulfilling the exact incentives of a profit-driven, unregulated industrial system. When we evaluate a technology solely by its immediate mechanical function and market success, we ignore the slow-moving planetary risks these examples revealed. In 1940, Midgley contracted polio. The disease left him severely disabled and paralyzed from the waist down. Confronted with this new physical constraint, the mechanical engineer immediately sought to build a solution to bypass it. He designed a complex mechanical system. By using a specific arrangement of ropes and pulleys attached to his hospital bed, Midgley could independently lift himself. On the morning of November 2, 1944, his wife found him entangled in his own invention. The very system he carefully designed to grant him mobility inadvertently tightened around him. He was tragically strangled to death. Thomas Midgley Jr. died precisely as he lived. He was undone by the unforeseen, fatal consequence of his own perfectly engineered solution.